Okay, so continuing with our problems, we're on page 5 now. There it is. Two blocks are joined by an inextensible cable as shown. If the system is released from rest, determine the velocity of block A after it has moved 1.75 inches. There's also a pulley here. Okay. Assume that the coefficient of friction, kinetic friction coefficient is 0.25. And the plane and between block A and the plane, and neglect the mass and friction of the pulleys. Okay, so what kind of problem is this? This one's a little more veiled. This is a chapter 12 problem. 13, 14, what do you think? I'll give you a big hint. By the way, that's probably supposed to be 1.75 meters in inches. Let's just make that change. So when you look at the packet, I apologize that it's in inches. We're going to work it as if it's meters. Same principle. What do you think? Chapter 12, forces. Chapter 13, energy.
11.
Chapter 14. Well, chapter 11, of course, right? Because we're going to have to deal with the rope. But we're interested in how fast the thing's moving, and obviously the friction force is going to play a role in that. The mass of block A and the fact that block B is dropping, all of that will play a part in this. It will help us determine the velocity after the thing has moved 1 3/4 meters. There's a dead giveaway here. Notice that the equations, chapter 12, look like this. Sum of forces is mass times acceleration. Chapter 13, basically energy. Chapter 14, momentum and impulse. Those are the basic equations, and I haven't put all the details on them, obviously. One of the key things to remember is that this equation involves force times distance. This equation essentially involves force times time. Whereas this equation is just talking about force and how it relates to the rate of change of velocity. Okay? Which one do you prefer to use? Which one is always the easiest? Energy. Should we use energy in this case? We were given a distance, not a time. So we should use energy. That would be ideal, right? Now you might look at this and say, well, that's all well and good, but I know that the friction is going to pull some energy out of it. How do I account for that? Well, couldn't you just multiply the friction force times the distance that was given? And that would quantify the amount of energy pulled out? Sure. So I'm going to select chapter 13 for this one because I think not only is it the easiest way to go, but I think it'll solve the problem. Now, you could use a rope equation here, but it's pretty easy to see what's going on, right? It's pretty easy to see that basically B is going to move down at half the rate of A, right? So basically, you could simply by inspection say that the acceleration of A is going to be twice the acceleration of B. That's pretty much all we really need. And we can write that the acceleration of A will be in this direction, the acceleration of B will be in this direction. We can set up the coordinate system however we want. When you're talking about energy, a lot of times the direction of the coordinate system is not all that important. Okay? So, what forms of energy do we have here? Well, let's start with our basic equation. The system starts at rest, so there's no kinetic energy initially. The system is moving in the final state, so let's attack T2 first. Let's take care of that part. In fact, let's just write it down up here. T2 is going to be 1/2 mass A, velocity of A final, plus 1/2 mass of B, velocity of B final. Now it looks like we've got two unknowns over here, but remember, we can also write that the velocity of A is going to be twice the velocity of B. Does everybody see why that is from inspection? If B moves down by 1/2 meter, And there's going to be a ½ meter gain of length down here. That ½ meter on each side comes up to a whole meter that A had to move, right? So there is a relationship between the velocity of A and the velocity of B. So basically there's one unknown on the right-hand side of this equation as far as we're concerned. Okay, let's go ahead and make it one unknown, because the question is really, what is the velocity of A? So let's just get rid of the velocity of B in favor of the velocity of A. So that would just be velocity of A over 2 instead of the velocity of B. Okay, to make it even easier, let's go ahead and rearrange the math a bit. Notice the velocity of A squared is a common factor here. So we're going to have 1/2 mass A plus, let's see, 1/4 of mass B multiplied by the velocity of A squared. All I did is I pulled out the velocity of A squared, realized I was left with 1/2 of mass A, and I've got 1/2 of mass B, but I've got 1/4 of it. Make sense?
Should that be just half mass A plus 1/4 mass B?
No, we've got this factor
Oh,
of half in
okay.
front of both of them. Good question. Please do check my math. I do make mistakes, so I appreciate that. So basically, the right-hand side is taken care of. So what forces do work on the system? Well, friction. Friction is going to do work. Anything else?
Gravity.
Gravity is going to do work. Notice we're not interested in saying that inertia does any work, right? That doesn't make any sense. The inertia, or the momentum of this stuff, is taken care of on the right-hand side in the kinetic energy. So that motion is taken care of. The fact that these masses begin to move, it takes force to make that happen, but we're not going to include that as if it's a force that acts on the system. Okay? So basically, all we have is friction and gravity. That's the only thing that goes in here, right? Now, if I write force times, and let's just call it, well, we've got that as a delta x already. There's the force that friction is going to apply to A. Okay? Should I write this as a positive thing or a negative thing? Well, it depends. Does the force act in the same direction? Does the frictional force on the block act in the same direction that the block moves? They're opposite, right? So when they're opposite, I've got to put a negative sign in front of them. Because the friction force is going to act in this direction, but the motion is going to be to the right. Okay? I don't need that mu in there. By the way, what is the friction? Well, the friction is going to be at its maximum, since it's the kinetic friction times the normal force, but summing forces in the y direction, you can see that we'll just have the weight of block A. So there it is. So we can say this is negative mu k mass A g multiplied by delta x. See how I expanded that frictional work into terms that I know, or at least can find. Now how about B? Well, don't we just need a negative mass of B times G times delta Y? Right? What's the relationship between delta Y and delta X? Well, that's just basically the relationship between these, and we already knew by inspection that the distance A moves is twice the distance B moves. Right? This is essentially the distance that A moves, and this is essentially the distance that B moves, but we have to be careful because B is moving down. B is moving in the same direction as the force, the weight acting on it. So this delta Y had better be negative, or we better flip this sign. Does that make sense? All I'm going to do is flip the sign and write that delta Y, which is for B, is going to be delta X over 2. Does that make sense? Basically, B is going to move down half of that distance. Okay. All right, so what do we have left? Well, then I'm running off the board, so let me just plug in numbers. So negative mu was 1/4. Mass of A, 30 kilograms. Acceleration of gravity G, 9.81 meters per second squared, multiplied by 1.75 meters, plus the mass of B, 90 kilograms multiplied by G, 9.81 meters per second squared, times 1.75 meters over 2. I'm running out of space, so I have to put my equal sign on the next line, equals T2. So that's 1/2 the mass of A, which is 30 kilograms, plus 1/4 of the mass of B, times the velocity of A final. Now, I should have gone ahead and rearranged this like I normally do, but I didn't, I forgot to. So what I'll do is just figure out this number and divide it by this number. Let's check the units and see if that makes sense. The kilograms on both sides of the equation can be canceled, and we'll end up with meters squared per second squared, which is correct for the velocity of A squared. Okay. So let's see what number we get. All right, take this term first, negative 0.25 times 30 times 9.81 times 1.75 plus 90 times 9.81 times 1.75 over 2. Okay, I've got a number for the left-hand side. I have to divide it by this, so basically I'll multiply by 2, and I'll divide by this. Divided by 30 plus 1/4 of 90. Okay, so I've got VA squared is 15,450 or so. Take the square root of that and say that the velocity of A, in here, the velocity of A comes out to 124 meters per second or so. I rounded it off. Okay? Any questions? We could do a sanity check and see if this makes any sense, right? Because if the block was just in free fall, it should go at a faster speed, right? In fact, the velocity of B is half the velocity of A. So let's just consider B. The velocity of B would be half of this, so that'd be what, 60, I can't think, 62? Yeah. Okay, so 62 meters per second. What would B do if it was in free fall? Well, that's just a chapter 11 question, right? Basically, all we need is V final equals V initial plus AT, but that's not going to help us because we don't have time, so let's try this one. V final squared equals V initial squared plus 2A delta X. Now, of course, since I'm talking about B, I'm going to be talking about delta Y instead of delta X. The initial is 0. The acceleration is just g. So the final velocity should be the square root of 2g delta y. How far does B move? Well, it moves half of that distance. So I guess I'll go ahead and show you what numbers I'm going to plug in my calculator. 2 times 9.81 meters per second squared multiplied by 1.75 meters over 2. I guess the 2's cancel mathematically, so that was handy. 9.81 times 1.75, square root of answer. I get 4 point some odd meters per second. What does that tell you about this answer? It's not right. There's no way. Right? Because if block B was just in free fall, it should be going faster. So probably I made a mistake in the numbers somewhere.
For VA, I got 7.345.
Here?
Yeah. Yeah, after you take the square root.
Okay. So maybe I plugged in the numbers wrong. So let's see.
That's a negative 0.25, right?
Sorry? Yeah, that's a negative 0.25. Does anyone agree with that? So I probably plugged the number into my calculator wrong. See how the sanity checks help? Okay, so how much did you get?
Yeah, 7.345.
Okay, that we'd have to divide by 2 to get the velocity of B, right? And it would come out to be less than the 4.14 that I got.
3.67.
So the velocity of B, 3.67 meters per second. I didn't intentionally make a mistake, but I probably did make a mistake in there somewhere. I don't know that there's a whole lot of value in going back to figure out where I made a mistake. I think the equation's right. I think I plugged a number in wrong. You guys want me to find it or go on? Sorry?
Go on.
All right, question 6.
You scroll forward.
The speed governor shown consists of a plunger that moves outward as the angular speed increases until it contacts switch S. When the angular speed is 0, the plunger is in the position shown and the force in the spring is 80 newtons. The stiffness of the spring is 400 newtons per meter. The 250 gram mass of the plunger may be considered to be concentrated at point G. The system lies in the horizontal plane. Determine the minimum value of the angular speed omega for which the plunger will contact the switch. Okay, can I erase this? What kind of problem is this? It's a hard one, right? That's what kind of problem it is. You see how there's basically going to be a forced balance between the spring and the plunger? So basically what has to happen is the spring will have to be, is it compressed? Yeah, it looks like it's compressed because you see the back side of this plunger is pushing on the spring. So the spring will have to be compressed 10 millimeters before the switch will be contacted. I sneezed the other day and I threw my neck out. Only 141, come on. Too early for this guy. So anyway, now the mass is already being accelerated. If this wheel is rotating around, the mass of this plunger is being accelerated this way by the spring, right? Basically the spring is pushing on the head of the plunger to keep it from flying outward. Now, the amount of force that would be in the spring when the plunger contacts the switch would be whatever the spring constant is times the deflection. Let's see, now what did they tell us? The plunger is in the position shown and the force in the spring is 80 newtons. So the spring is already applying 80 newtons of force. The stiffness of the spring is 400 newtons per meter. So that's, what, if we divide by 1,000, that's 0.4 newtons per millimeter. So how much force would be in the spring if the spring is compressed by another 10 millimeters? Yeah, 84, right? Because it's 10 times 0.4, so it'll be 84 newtons. Does that make sense? Everybody see why the force in the spring is 84 newtons? Okay. Now that would be the force that would be applied to this plunger when it reaches the switch. Now, since force is equal to mass times acceleration, what kind of acceleration does the plunger have? Does it have a tangential acceleration or a normal? Bless you, a normal acceleration. Which one? Well, if the wheel's rotating around, then it just has a normal acceleration, right? We're going to get up to some speed. So we're only interested in the normal acceleration anyway, because it's only the normal direction we're interested in. The tangential direction doesn't make any difference, right? The force balance you're talking about is a force in the normal direction. So basically, the question is, what normal force or what normal acceleration would we get? Well, it'd just be the force divided by the mass of the plunger. Okay? Now, the force divided by the mass of the plunger, we could put a number in here, but that would be the normal acceleration. What's the normal acceleration? Well, it would be the tangential velocity squared divided by the radius of curvature. What's the radius of curvature? Well, if this point moves out 10 more millimeters, then the radius of curvature is 100 millimeters. See that? Or 0.1 meters. So we're not interested in the outer edge of the wheel and how fast it's moving. We're interested in the velocity of the center mass of this plunger, which is now out at a row of 0.1 meters. Right? But this is probably not the most convenient form of the equation. Remember that velocity is omega r, or rho. And so velocity squared is omega squared rho squared. So we can plug that in here and say that this is just omega squared times rho. See how the rho squared cancels with one of the rho's? Okay. So let me just write it that way. This is omega squared rho, and then realize that omega is just, let's see, F over rho m square root. So let's see what we get. So omega is the square root. The force is 84 newtons. The radius is 0.1 meters, right? Because we just discussed how this center of gravity would be out at 100 millimeters, which is 0.1 meters. And the mass is just the mass of the plunger. The plunger is a 250 gram mass, so that's 0.25 kilograms. Now a newton is just a kilogram meter per second squared, so the kilograms go away, and the meters go away. So do you see how we'll get per second units out of this? So it would be radians per second. All right, so 84 over 0.1 would be 840 divided by a quarter, and square root. This should be 57.97 or so radians per second. I had to round up. Does that make sense? I went through that one pretty quickly. Any questions on it?
This is on video.
This is on video, yes. You're welcome to ask questions. It's just you guys that are going to see the video. Or do you mean we're all lost, we have no idea, but we can go back and hit play on the video? Okay. Problem 7. We still have 15 minutes, so let's go through as many as we can. Problem 7. Given an aircraft carrier travels at 40 kilometers per hour and uses a steam catapult to aid in launching a 7 megagram jet fighter into the air at 200 kilometers per hour. The speed must be achieved in 5 seconds, and the jet produces 70 kilonewtons of thrust during the launch. The force applied from the carrier onto the plane is given by the graph shown, and we're supposed to find the peak force F naught that must be applied to the jet plane. Okay? What kind of solution strategy do you think we should employ here? Look at the graph. What do we have? On the y-axis we got force. On the x-axis we have time. Chapter 12, 13, or 14? Impulse momentum, because we've got force over time, right? In fact, we could calculate the total impulse on the jet from the graph, except that we don't know this force. So let's write it in terms of F naught, right? If we knew F naught, then we could calculate the area of this triangle and the area of this triangle. And how would that look? Well, it would look like this. It would be, and so we're just basically evaluating this integral and getting the area under the curve. Well, it would be F naught, which is the height of the triangle, times 2 divided by 2. So that would be the area over here. Plus F naught for this triangle, we need 2 to 5, which is 3 over 2. So if we add this up, it would be F naught times, what, 5 over 2? That's the area there. So that's the area underneath that triangle. Now notice that that's not the only force applied to the jet. The jet produces 70 kilonewtons of thrust during the launch, right? So if the jet produces 70 kilonewtons of thrust over 5 seconds, that's another impulse we have to consider, right? So why don't we, so this is from the catapult. But from the jet, the evaluation of this integral would be 70 kilonewtons times 5 seconds. So we can get an actual number there, right? So 70 kilonewtons multiplied by 5 seconds, well, 70 times 5 would be 350. kilonewton seconds worth of impulse. Okay, I did the math right. I think I did. Now the jet has to end up at 200 kilometers per hour. Okay? And the jet has a mass of 7 megagrams. But notice the aircraft carrier is already traveling at 40 kilometers per hour, right? So the extra speed that the jet needs is only an extra 160 kilometers per hour. In fact, basically we're dancing around the impulse momentum equation now, where if we consider just the jet by itself, the mass of the jet multiplied by the initial velocity of the jet plus all of the impulse acting on the jet equals the mass times the velocity final of the jet. Notice we already have all of this. At least we have one number plus one that's an unknown thing, right? So basically, the mass of the jet times the initial velocity of the jet. Let's see, how should we do this? We're looking for this force, so let's just plug in the equation. Let's see, plus, let's just call this T, the thrust from the jet, or the impulse of the thrust from the jet. So plus T plus F naught 5/2 equals mVA final. The only unknown now is F naught, so let's solve for it. So if we solve for it, F naught equals, let's see, we'll do it this way. First thing I'm going to do is move these two positive terms to the other side. Mass VA final less mass VA initial minus T. So I move these terms to the other side and then multiply through by 2 over 5. Okay? So, pulling out the mass of the jet, it's 7 megagrams, so that's 7,000 kilograms. The final velocity of the jet is 200 kilometers per hour. So, not crazy about the units. Let's subtract off the initial 40. We have kilometers per hour. I'd like to have 1 hour per 3,600 seconds. And 1,000 meters per 1 kilometer. Okay, so that takes care of this part so far. We've taken care of those two terms. Minus the thrust. Do you remember the impulse of the thrust? I've erased it. It was 350 kilonewton seconds, right? So that's T, and we need 2/5 of this. Now let's see if our units are consistent. We've got a kilogram meter per second, but here we have kilonewtons. So let me cheat, get rid of the K, and put in 3 zeros. So then we have Newton seconds, and now our units are consistent. Okay? Let's plug this into our calculator and see what we get. 7,000 times 160. Let's see, that's this term times 1,000 divided by 3,600 less 350, 3 zeros times 2 divided by 5. What number do you guys get?
Negative 15,555.
How's that? Okay. Now what happened? Where did the units go? There's two problems here. We had Newton seconds, and now I've just written this as newtons. Where did the seconds go? Remember when we wrote F naught times, basically when we calculated this area, we already had time on the x-axis. So this term here, this 2/5, actually has units with it, right? It actually has units of inverse seconds. Because this 5 has units of seconds. That's where these 5 seconds came from, right? The 2 was from the fact that we're dealing with triangles and had to cut the area in half. An easy way to see this is A similar triangle would be here, a similar triangle would be here. So just calculate the area of the rectangle, 5 times F naught divided by 2, and you've got the area. Right? Why is it negative? That's the real question. Why is F naught negative? I thought it should be positive. I thought that the ship should be pushing. Does that mean that it really is pushing and somehow we got the sign wrong? No, we wrote the equation down correctly. Right? This is a vector equation. We expected the force on the plane to be to the right. We expected the initial velocity and final velocity of the plane to be to the right. What happened?
Force on the boat.
No. We're not concerned with the boat, we're concerned with the motion of the airplane. What happened is the jet develops more than enough thrust to take off on by itself. It doesn't need the ship's help. It doesn't need the catapult. So basically the catapult would have to pull back on it, otherwise it's going to take off in less than 5 seconds. Maybe this is the great F-35 that we keep pouring money into, I don't know. We don't need steam catapults anymore, who knows?
So
What it really means is that I probably set up the problem wrong. What's that?
we took the jet with respect to the water
With respect to ground, yes.
rather than with respect to the boat.
And you may look at it and say, well, then, is it really valid because some of the force comes from the boat and some of the force comes from the jet? The jet's pushing on the air, whereas the same catapult is pushing on the boat, right? But it doesn't really matter. It doesn't matter where the force comes from. All that matters is that a force is applied to the jet. I don't care if it slows down the aircraft carrier. It doesn't matter. Good questions. Anything else? We've got 5 minutes. Can I use the 5 minutes effectively to solve one more problem? Probably not. That would take a little longer than 5 minutes. Question 8. What I'll do is solve the remaining of the questions, 8 through 12, and post them on YouTube for you as well, okay? Good luck on the exam, guys.